Hello and welcome to this new video where we discuss mathematics and physics. This particular video is just a follow-up from a previous video that I've done where we've done the mathematics, or at least we've done one way of explaining why the sum of all positive integers can be assigned the value minus 1/12. Okay, and for this we had used a so-called regularization method, whereby on the one hand we try to disentangle the diverging part from a non-diverging part, and then we subtract the diverging part from the diverging series of the sum of all integers, and we get a final number, which is minus 1/12. Okay, and we are going to see how, from a physical standpoint, this actually has an importance to provide ground for what we call the Casimir effect. Right, so here basically what we are going to look at is a sort of toy model. But before I actually go into any details, I just want to emphasize a few things. The Casimir effect is actually a very, very general effect. It's going to work in various circumstances, but in fact, in principle, it's supposed to work for any kind of wave, um, uh, for any kind of wave behavior that can occur in a stationary fashion between two media, for example, or between two specific kind of boundary conditions. So that's the first aspect. The second aspect has to do with the fact that you want to have some sort of averaging, so some sort of thermal motion, so some sort of fluctuations occurring in your system. So you want these waves to be somehow fluctuating. And this can occur in various fashions. This can occur through thermal motion of the medium you're looking at, and in which case you're going to get a thermal Casimir effect. And it can also occur due to quantum fluctuations. And you can also have a combination of both. And that's kind of most modern theories to try to look at how do we deal with both together. Now, aside from this, there is also an aspect having to do with the fact that if you are not dealing with electromagnetism, or you are dealing with electromagnetism in a medium, okay, then the waves you're looking at, or the electromagnetic waves you're looking at in a medium, they may actually have what is called a screening. So what that means is that they are not going to have an infinite reach when it comes to interactions. They are going to somehow decay in magnitude over some length of space. And if that happens, then your interactions are going to work only at short range. So when you bring the inclusions or defects in your medium as close as you can together. In case you can't do that, then what's going to happen is that either the interactions are going to die off, or basically you need to look for situations where these interactions are allegedly going to infinity. And in fact, that's something that was put forward, I think, by Michael Fisher and Deugène, Pierre-Gilles Deugène, who in a paper actually described from the original work of Casimir, that was in the context of quantum electrodynamics between two metallic plates, they actually showed that the very same phenomenon could occur basically in what I call binary mixture at the critical point, whereby at the critical point you expect the so-called correlation functions between any two density, let's say, at two different places to actually be infinitely correlated. So correlated at infinite distance, that's rather what I mean. And so in that case, you can get a very Casimir-like effect in such systems. Anyway, that was just to put a little bit of context. And so what I'm going to discuss here has to be viewed in that context. I'm talking about something that is fluctuating. I'm going to assume that there is no particular length scale in my system, but that's something that could be added to it. And basically there you go. We are going to look at this. We are going to look at the quantum case, but it's not necessary. We could also look at the thermal case as well. So essentially, we look at a sort of 1D toy model, but this 1D toy model could be kind of realistically done, in experiments and so on. It's not like it's something that doesn't exist. And it's as follows. So we just imagine that we've got a sort of medium or field that can have stationary waves between two positions. So x equals 0 and x equals L, for example. And a stationary solution, by definition, in that case, is going to look like that. It's just so that you've got, we don't need it per se, but it's just so that you get some idea. So a sine of kx and then cosine of omega t. That's the definition, by the way, of a stunning waves, is when you've got this sort of decoupling or factorizability of the wave solution, so that basically it's not propagating anymore, and you've got fixed nodes that basically have zero amplitude at all times. This is characterized by this, basically, by this part. Okay? Now, if it's a wave, and we are just assuming that this is a standard solution to the linear wave equation, then you've got what is called the dispersion relation that relates omega, the frequency of oscillation, to k, the kind of wave mode of oscillation. And this is omega is equal to c times k, and c is what we call the celerity of the wave. This celerity, of course, when you talk about light, is going to be the speed of light in vacuum. If you talk about something else, usually that's going to be the speed of sound or the speed of displacement of the wave. Now, we've got BC here, stands for boundary conditions, and I said that we want null boundary conditions. So what that means is that we want that sine of k times 0 is equal to 0, and sine of kl is equal to 0. Now, the only possibility for this to be true is actually for the k values to take only discrete kind of values that are clearly specific. And this is called the quantization of modes of oscillation. This quantization has nothing to do with quantum mechanics, but in quantum mechanics, the quantization comes from there. So we should not kind of invert like the causation. The quantization in quantum mechanics comes from specific boundary conditions on a wave function, and these boundary conditions are going to entail a quantization. So there's nothing special, in a sense, with the quantum realm. If you take any kind of guitar string, you're going to get quantization of the mode oscillation. So that's basically what it is. So these quantizations are Kn is equal to n pi over L, where n simply samples all possible integers. Now we need to be very careful here. The n value corresponds to a mode of oscillation. Okay, so it's going to be associated to a different frequency. Okay, so I'm going to illustrate this at the bottom. So I give 3 possible cases. Of course, there are infinitely many of oscillation. So first, we've got the first mode of oscillation that is going to go back and forth, where you've got here the maximum, and the maximum is going simply to oscillate like this. And then the corresponding frequency is c pi over L. Now, the second mode of oscillation has a node here that is going to never move. That is basically stuck at 0. And then you've got 2 kind of wobbly parts that are on the left and right of that node. Then n is equal to 3. You've got basically 3 parts that are oscillating. And each time the frequency is actually going to change. Here is actually twice omega 1, and here is 3 times omega 1. So the frequencies are different. Now, once we have said that, we know that for a given frequency, omega, we had seen, and I will put a link there, the quantum vacuum fluctuations. So assuming that quantum vacuum fluctuations are going to matter for that system, the quantum vacuum fluctuation give rise to a non-zero ground state energy. So although it's an oscillator, you can't have that set to zero. So basically, for example, here you could imagine set A to zero. That's still a possibility in this particular classical treatment. What the quantum, basically vacuum fluctuation kind of tells you that you can't set this A to zero actually. And so the quantum vacuum, the frequency omega, the quantum vacuum fluctuations give rise to a non-zero ground state energy or lowest energy. And this is basically equal to, let's say, E0 of omega is equal to half h bar omega. Okay? So that's for one oscillator that oscillates at frequency omega. And that's the ground state energy. Now, the definition of the vacuum is precisely that. The vacuum is when all possible modes of oscillation are in their ground states. So vacuum equal all modes in their ground state. Okay? But what that means is that we can calculate, therefore, the energy of the vacuum. And so we are going to look at then the energy of the vacuum is going to be equal. So essentially I've got half of h bar omega, but for all of them, okay? For all the frequencies that I have here. So basically it's the sum for n ranging from 1 to plus infinity, just basically sticking that here. And then half h bar omega n, and this is equal to, I can actually say half h bar, and then the sum n is equal 1 to plus infinity, and then omega n is equal to ckn. So basically I'm kind of getting there, so that's h bar c pi over L, and then sum n equal to 1 plus infinity of n. And here we actually get that this thing is actually infinite, okay? So what we get is that this thing is infinite because this sum diverges. Okay, and so what we need to do is regularization. So what we do is that we define evac tilde, and evac tilde is going to be equal by definition. So that's a definition to the vacuum energy. By the way, this is vacuum energy at the distance L between the different lines, and then minus, and here I'm going to call that minus minus the limit when alpha tends to 0 of 1 over alpha squared. And in fact, I made a slight mistake. Evac and then minus, so I need to put all of that. So that's h bar c pi over 2l, and then limit when alpha tends to 0 of 1 over alpha squared. And basically this is going to be so I subtract here the infinite contribution from the infinite and diverging part to these modes, and basically I'm going to get that this is, I've replaced that, and here I'm going to write evac. If you want, you can write reg for regularized, and that's going to be minus h bar c pi, and then divided by 24L. Okay, and basically that's it. So you get and it's done. So that's basically like the Casimir energy. So this Casimir energy, okay, and this Casimir energy is basically telling you that if you've got a vacuum, so again, vacuum here is to be understood as the ground state of all possible oscillators in your system, then you're still going to have an interaction between two plates. Okay, that's the definition of the vacuum. So we need to be a bit clear. It doesn't mean there is nothing. What it means is that all the oscillators are in their ground state, and so in that case, you do get an interaction, which is this one. So basically, that's kind of how it works. So we just remove an infinite term. Okay, we subtract an infinite term from a pre-existing one, and then we see what happens. Sometimes the way to conceive this subtraction here is basically as if we were subtracting the energy the plates would have if we were to put them infinitely far apart as well. And we can understand in that sense that we have more frequencies to sample in that case. And basically that's kind of how that would work. But whatever the case, the point here is that we regularize, we get rid of the infinity, and then we get this particular energy, which is attractive. So we get that there is an attraction between these plates simply through vacuum fluctuations of the oscillation modes. Okay, so basically that's it. If you've got any questions or comments, by all means, do let me know in the comment section, and otherwise see you in the next video.